Hi everybody, welcome to Dr. Manny's YouTube Learn Shops. This is part 3 to Descriptive Statistics, which deals with probability distribution. The objectives for this session are to describe the characteristics of a normal distribution and use a standard normal distribution to obtain z-scores and percentiles. As we've mentioned previously, descriptive statistics describe, present, summarize and organize data, either through numerical calculations or graphs or tables. Descriptive statistical analysis helps researchers to understand data, and doing a descriptive statistical analysis of the data set is crucial. Numerous researchers, as I've indicated previously, omit this part and therefore lose valuable insights about their data, which often leads to wrong conclusions. So when we talk about variables, there are random variables. In probability and statistics, a random variable is a value subject to variations due to chance. Is a variable taking on numerical values determined by the outcome of the random phenomenon, such as a possible outcome as a roll of a dice? It can be classified as either discrete, that is, taking any of a specified list of exact values, or as continuous, taking any numerical value in an interval or collection of intervals. The mathematical function describing the possible values of a random variable and associated probabilities is also known as a probability distribution. Discrete random variables. These can take on either finite or at most a countable infinite set of discrete values. For example, integers such as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Their probability distribution is given by a probability mass function which directly maps each value of the random variable to a probability. The probabilities must satisfy two requirements. Every probability is a number between 0 and 1. And the sum of all probabilities is 1. Examples: the values obtained from rolling a dice, or the grades received on a test out of 100. In this diagram, it shows the probability mass function of a discrete probability distribution. The probabilities of the integers are 1, 3 and 7, or respectively 0.2, 0.5, 0.3. A set not containing any of these points has potentially a probability of 0. Discrete random variables. Examples of discrete random variables are as follows. A discrete random variable has a countable number of possible values. The number of eggs that a hen lays in a given day, the number of people going to a soccer match on a given day, the number of students that come to class on a given day, the number of people at McDonald's on a given day and time. It cannot be 3.3 or with a decimal. Continuous random variables can take on any value with an interval. It has an uncountable infinite number of possible values, all of which have a probability of 0. Though ranges of such values have a non-zero probability, the resulting probability distribution of a random variable can be described by a probability density function, where the probability is found to be taking the area under the curve. For example, selecting random numbers between 0 and 1 are examples of continuous random variables because there are an infinite number of possibilities. Continuous random variables, look at the diagram. It shows the probability density function of a normal distribution, also called the bell curve. the most important continuous random distribution. As notated on the figure, the probabilities of intervals of values corresponds to the area under the curve. Examples of continuous random variables are as follows. A continuous random variable is a variable whose value is numerically an outcome of a random phenomenon obtained by measuring. In general, quantities such as pressure, height, mass, weight, density, volume, temperature, distance are all examples of continuous random variables. So then we need to look at probability distribution. And a probability distribution is a statistical function that describes all the possible values and possibilities that a random variable can take within a given range. This range will be bounded by the minimum and maximum possible values, but precisely where the possible value is likely to be plotted on the probability distribution depends on the number of factors. These factors include the distribution's mean, standard deviation, skewness, and kurtosis. Divergence, skewness, kurtosis. When we look at probability distribution, it's a formula or a table that's used to assign probabilities to each possible value, random variable x. The probability distribution may be either discrete or continuous. A discrete distribution means that the x can assume one of a countable, usually finite, number of values, while a continuous distribution means that x can assume one of an infinite, uncountable number of different values. Normal probability distribution is formed from all possible outcomes of a random process for a random variable x and the probability associated with each outcome. Probability distributions can be discrete with a distinct number of outcomes such as the number of children, or continuous, a continuous outcome such as height or weight. A probability density function is defined such as the likelihood that value of x between a and b equals the integral, which is the area under the curve between a and b. A normal probability distribution is symmetric and centered on the mean, the same as the median and the mode. While the x-axis ranges from negative infinity to positive infinity, nearly all the x values fall within plus or minus 3 standard deviations of the mean, which is 99.7 of the values, while 68 are within plus or minus 1 standard deviation and 95 are within plus or minus 2 standard deviations. This is the 3 sigma rule, or the 6, 8, 9, 5, 99, 7 rule. An example of probability distribution is when rolling 2 standard 6-sided dice, each dice has 1/6 probability of rolling a single number, 1 through 6, but the sum of the 2 dice will form the probability distribution depicted in the figure. 7 is the most common outcome, 1 plus 6, 6 plus 1, 5 plus 2, 2 plus 5, 3 plus 4, 4 plus 3. 2 and 12, on the other hand, are far less likely, 1 plus 1 and 6 plus 6, to occur. So, when we look at discrete probability distributions, examples commonly used in statistics are binomial distribution, hypergeometric distribution, and Poisson distribution. In binomial distribution, this is simply the probability of success or failure outcome in an experiment or survey that's repeated multiple times. It's got 2 possible outcomes, that's why we have bi. An example would be a coin toss has only two possible outcomes, heads or tails. A test could have two possible outcomes, pass or fail. When we look at hypergeometric distribution, this describes the possibility of success. There's a formula. An example would be a deck of cards contains 20 cards. 6 red cards and 14 black cards. 5 cards are drawn randomly without replacement. What's the probability that exactly 4 red cards are drawn? The probability of choosing exactly 4 red cards is P. 4 red cards equals the number of samples with the number of red cards and 1 black card being the possible outcomes. In shorthand, the formula can be written as follows, the solution as such. The Poisson distribution is a discrete distribution that measures the probability of a given number of events happening at a specified time. Examples could be the number of cases of diseases in a town, the number of mutations of a virus in a given region, the number of dolphin sightings in a given region, the number of births per hour during a given day. An example of discrete probability distribution would be you roll a die. If you roll a 6, you win a prize. You could roll a 1, 2, 3, 4, 5 or 6. All of the die rolls have an equal chance of being rolled, 1 out of 6. This gives you a discrete probability distribution, rolls 1, 2, 3, 4, 5, 6, odds 1 in 6 chances. Continuous probability distribution. This is a probability distribution in which the random variable x can take on any value. It's continuous. Because there are infinite values that x could assume, the probability of x taking on any one specific value is 0. The normal distribution is one example of continuous distribution. The probability that x falls between two values a and b equals the integral area under the curve from a to b, which is also your z-score. An example of continuous probability is estimating the weight of a person. You could guess that the mean weight is 150 pounds or 210 pounds or 185.5 pounds or any fraction of a pound, 172.566 pounds. The possibilities are infinite. In reality, you wouldn't estimate 160.111111 pounds, but it doesn't really change the fact that you could. So that is why it's a continuous probability distribution. When we look at probability distribution, we have to look at what is called the expected value. And the expected value is the average value of random variables, and it indicates the probability weighted average of all possible values. If we assume the experiment to be a game, for example, the random variable maps game outcome to winning amounts and its expected value, thus represents the expected average winnings of a game. Now, there's no difference between the mean and the expected value. They are two names for the same thing, but tend to be used in different contexts. The expected value is related to the random variable, the mean to a sample population or probability distribution. But basically, they're the same thing. The basic formula for expected value is, the first variation of the expected value formula is the expected value of one event repeated several times. Think about a coin toss. In such a case, the expected value can be found using the following formula. EV, expected value, P, the probability of the event, the number is N. The formula changes slightly according to what kind of events are happening. For most simple events, you'll either use expected value formula of the binomial random variable or the expected value formula for multiple events. Here's an example of the expected value. To calculate the expected value for a single discrete random variable, you've got to multiply the value of the variable by a probability of that value occurring. So, for example, a normal six-sided die, once you roll the die, it has an equal 1/6 chance of landing on 1, 2, 3, 4, 5 or 6. Given this information, the calculation is straightforward, as you can see. If you were to roll a die, a six-sided die, an infinite amount of times, you see the average value equals 3.5. In a standard normal distribution, we look at what is called the Z distribution. And a standard normal distribution can also be called a Z distribution. And it's a special normal distribution where the mean is 0 and the standard deviation is 1. Converting a normal distribution into a Z distribution allows you to calculate the probability of certain values occurring and to compare different data sets. The Z-score. When you compare the normal distribution, all normal distributions, like the standard normal distribution, are unimodal and symmetrically distributed within a bell-shaped curve. In the standard normal distribution, the mean and standard deviation are always fixed. The mean determines where the curve is centered. Increasing the mean moves the curve right, while decreasing it moves the curve left, skewing it. The standard deviation manipulates the curve, and a small standard deviation results in a narrow curve, while a large standard deviation results in a wide curve. So examples of normal distributions. Standard, squeezed basically means narrow, stretched basically means broadened, shifted right, shifted left, skewed left. When you standardize a normal distribution, the mean becomes 0. The standard deviation becomes 1. This allows the calculation of probability of certain values occurring in the distribution, or to compare data sets with different means and standard deviations. While data points are referred to as x in a normal distribution, they are called Z or Z-scores in the Z distribution. A Z-score is a standard score that tells you how many standard deviations away from the mean an individual value lies. A positive Z-score means that the x value is greater than the mean. A negative Z-score means your x value is less than the mean. A Z-score of 0 means your x value is equal to the mean. So when you convert a normal distribution to a standard normal distribution, this allows you to compare scores on different distributions with different means and standard deviations. Normal scores for statistical decision making, example, grading on a curve. Finding the probability of observations in a distribution falling above or below a given value. Or finding the probability that a sample mean significantly differs from a known population. So when you calculate a Z-score, why are you doing it? And this is to standardize a value from a normal distribution to convert the individual value to a Z-score. You subtract the mean from the individual value and you divide the difference by the standard deviation as in the formula. However, there are apps that you can access online which will do this for you. Here's an example for finding the Z-score. You want to collect the SAT scores from students. The data follows a normal distribution. The mean score M is 1150. Standard deviation 150. You want to find the probability that SAT scores in your sample exceed 1380. To standardise your data, you first find the Z-score for 1380, and the Z-score tells you how many standard deviations away from 1380 it is from the mean. So, step 1, subtract the mean from the X value. Step 2, divide the difference by the standard deviation. The Z-score for a value of 1380 is 1.53. That means 1380 is 1.53 standard deviations from the mean of your distribution. The standard normal distribution is the probability distribution. So the area under the curve between the 2 points tells you the probability of variables taking on a range of values. So the total area under the curve is 1 or 100%. Every Z-score has an associated p-value that tells you the probability of all the values below or above that Z-score occurring. This is the area under the curve left or right of the Z-score, and the p-value means the probability. For a given statistical model, the smaller the p-value, the greater the statistical incompatibility of the data within the null hypothesis. So the area under the curve is the standard normal distribution. Z-tests and p-values, well, the Z-score is a test statistic and it's used in a Z-test. The Z-test is used to compare the means of two groups or compare the mean of a group to a set value. The null hypothesis typically assumes no difference between the two groups. The area under the curve to the right of the Z-score is the p-value, and it's the likelihood that your observation occurring if the null hypothesis is true. Usually a p-value of 0.05 or less means that your results are unlikely to have arisen by chance. It indicates a significant statistical effect. By converting a value in a normal distribution to a Z-score, you can easily find the p-value for a Z-test. Here's an example of a normal distribution, a Z-table. A Z-table, that's the standard normal table, and it's a mathematical table that allows the percentage of values below to the left, a Z-score in the standard normal distribution. A Z-score, also known as a standard score, indicates the number of standard deviations a raw score lays above or below the mean. When the mean of a Z-score is calculated, it's always 0, and the standard deviation, which is the variance, is always in increments of 1. So, using a Z-table, when you use the Z-score, then you look at the Z-table for the corresponding probability. In a Z-table, the area under the curve is reported for every Z value between -4 and 4 intervals at 0.01. The Z-table allows the total area under the curve up to be a given Z-score. This area is equal to the probability of values below the Z-score occurring. The first column of a Z-score, take note, in a Z-table contains the Z-score up to the first decimal place. The top row of the table gives the second decimal place. When you're using a Z-table to find the corresponding area under the curve probability for a Z-score, go down to the row with the first 2 digits of your Z-score. Then go across the column with the same 3rd digit as your Z-score. Find the value at the intersection of the row and column for the previous steps. An example of the Z-table to find probability. The previous calculated SAT score of 1380 has a Z-score of 1.53. Using the full z-table, the z-score is 1.53, the p-value is 0.937. This is the probability that the SAT scores being 13, 80 or less, 93.7%, and its area under the curve left of the shaded area. To find the shaded area, you take away 0.937 from 1, which is the area under the curve. The probability of x greater than 1380 equals 1 minus 0.937 equals 0.063. That means it's likely that only 6.3% of the SAT scores in your sample exceed 1380. If we're using Z distribution as an example, the standard normal distribution is also known as the Z distribution. And it's the normal distribution within the mean of 0 and a standard deviation of 1. And we already said it's often called the bell curve because the graph of its probability density looks like a bell. An example would be, as a healthcare professional, you're interested to find out whether sleep habits have changed during the COVID-19 lockdowns. Before the lockdown, the population mean was 6.5 hours sleep. The lockdown sample mean is 7.62. To assess whether your sample mean significantly differs from the pre-lockdown population mean, you perform a z-test. Calculate a z-test for the sample mean value. Then find the p-value for your z-score using the z-table. Step 1 involves comparing sleep duration during and before the lockdown. You convert your lockdown sample mean into a z-score using the pre-lockdown population mean and standard deviation. A z-score of 2.24 means that your sample mean is 2.24 standard deviations greater than the population mean. Step 2, you want to find the p-value. To find the probability, p-value, of the sample mean z-score of 2.24 or less occurring, use the z-table to find the value at the intersection of row 2.2 and column 0.04. The table shows that the area under the curve up to or below your z-score is 0.9874. This means that your sample's mean sleep duration is higher than about 98.74% of the population mean sleep during the pre-lockdown. Find the p-value. To calculate the area under the curve above or right of the z-score is 0.9874. Since the total area under the curve is 1, subtract the area under the curve from your z-score. That's 1 minus 0.9874, which is equal to 0.0126. To find the p-value, to assess whether the sample differs from the population, calculate the area under the curve above or to the right of your score. Since the total area under the curve is 1, subtract the area under the curve below your z-score from 1. P-value of less than 0.05 or 5% means that the sample significantly differs from the population. So the probability of Z being greater than 2.24 equals 1 minus 0.9874 is equal to 0.0126 or 1.26%. With a p-value of less than 0.05, you can conclude that the average sleep duration in the COVID-19 lockdown was significantly higher than the pre-lockdown average. So in summary, a probability distribution is just a list of outcomes and their associated probabilities. Probability distributions come in many shapes with different characteristics as defined by the mean, standard deviation, skewedness and kurtosis. Random variables in probability have a defined domain and they can be continuous or discrete. Probability distributions summarize the relationship between possible values and their probability for a random variable. Okay, that concludes this session in an introduction to the basics. There are 7 other parts to this basic statistics learn shop. And remember, it is just the basics. And you can get access to a lot of other information on some of the excellent YouTube videos. See you in the next session, and if you think this has been of any value to you, or any of the other Dr. Manny Learn shops, recommend them to your friends and colleagues. Thanks, see you soon.